In this video, we're going to take a look at alternating series. So let's start by just defining what an alternating series is. An alternating series is a series n equals 1 to infinity, -1 to the n plus 1 times some sequence an, which if we were to write that out would mean that each sequence value is alternating between positive and negative. So an alternating series is just one where every single sequence value alternates between positive and negative, so we're adding and subtracting alternatively. So the alternating series test tells us that if we have this alternating series, that it will converge if the following conditions are met. 1. The sequence, ignoring the -1, the part that makes it alternate, if that is greater than 0, if the terms are eventually non-increasing, and if the limit of that sequence is equal to 0. So again, the alternating portion comes from that -1 to a power, and it doesn't have to be the n plus 1 because, again, we can always start at any point and just find those first n terms and then look at the series from there. But we see that we have that alternating component, and then we have some other sequence behind it. We need these three conditions to be shown true. I will say that there are other ways to get series to alternate. We've seen that sine and cosine can do it as well. So again, alternating series, we just need to have this pattern of adding and subtracting negative terms. We could also have a -2 to the n. -2 to the n, and of course, is just -1 to the n times 2 to the n. So again, different ways to get there, but we need to have something that's alternating between positives and negatives. So let's determine if the following series converges or diverges. We have the series from n equals 1 to infinity of -1 to the n plus 1 over n. Now remember that we talked about absolute convergence earlier, and the way that we show that is by taking the absolute value of the sequence and looking at what happens to that series. A lot of times we're going to be asked to show if a series converges, if it converges absolutely, if it converges conditionally, or if it diverges. If we just jump to the alternating series test, the best the alternating series test can show us is that it converges conditionally. We want to exclude that option of it converging absolutely. A lot of times the best course of option is actually to start with that absolute convergence. It depends, right? It depends on what the problem is asking for. Here, all it says is, does it converge or diverge? It doesn't specify. So, in fact, I might actually choose just to jump right into the alternating series. It's clearly an alternating series. We see that -1 to a power. And so maybe I just want to jump right into the alternating series test. But I'm going to just show you how we can show that this series actually does not converge absolutely, but it does converge conditionally. So of course, if we were to take that absolute value, we'd have the series from n equals 1 to infinity of 1 over n. This is a divergent series because it's a harmonic series. So this series, our series that we started with, n equals 1 to infinity of -1 to the n plus 1 over n, does not converge absolutely. That does not mean it doesn't converge in some other way, being conditionally. So anytime I see that -1 to a power, a great place to start, if it doesn't converge absolutely, is to just jump right into the alternating series test. So with the alternating series test, what we're going to consider is the an. The an is the portion without the -1 to a power, the portion that's not alternating. So the an would be equal to 1 over n. So we've got to show all three conditions are true. First, is 1 over n greater than 0? Well, of course it is. For all n equal to 1, that is obviously a true statement. 2, we need to show that those an's are eventually non-increasing. There's two ways to do that. We want to show that they are decreasing or constant. We can do that either through a derivative, or we can think about what happens between the 1 over n term plus the next term. So I compare 1 over n to the next term. Well, if we make the denominator bigger, it makes the fraction as a whole smaller. So what we see is each term after the first, if we start with 1 over n and go to the next term, that first term was bigger, meaning that this series, this sequence, is decreasing. So the second point checks out. Another way to see that, we know that n plus 1 is greater than n, so flipping it, well, those things have to be getting smaller as they go along. And finally, again, we can check it through a derivative. If we called the function 1 over x, well, then the derivative would be negative 1 over x squared. Of course, this is strictly decreasing because the 1 over x squared is going to have to be positive, and then it has a negative in front of it. And so that has to be strictly decreasing. So we know that this is a decreasing sequence. And then the third thing would be to show that it is the limit of the sequence is going to 0. So take the limit as n approaches infinity of 1 over n, and that is in fact equal to 0. So here we have kind of an interesting case. It looked very much like the harmonic series at the start, and if we took the absolute value, if we tried to take the absolute, if we looked at absolute convergence, it did not. It was comparable to the harmonic series. But the fact that it's alternating, now we actually have a convergent series. Somehow as this harmonic series alternates, remember that harmonic series, we were just adding the series of 1/2. We worked that out a few videos ago. By alternating it, we're canceling off certain values in a way we're no longer adding 1/2 infinitely. And so the series n equals 1 to infinity of negative 1 to the n plus 1 over n converges conditionally through the alternating series test. And you can abbreviate the alternating series test AST. Did we have to show that it converged? Didn't converge absolutely? Not per the instructions. Again, the instructions were, does it converge or diverge? We may be asked to show if something converges absolutely, which is why I think it's helpful to start there. If you start with the alternating series test and you're asked if it converges absolutely, you're going to have to go and show this step anyways. So if you can show that it converges absolutely, you're done in just this one step here. If you're asked to show it converges absolutely conditionally, start with the absolute, then go on to conditional, and then if it still diverges, it'll diverge. But it is helpful to start with that absolute convergence. If all we're asked to do is it convergent or is it divergent? Well, we could jump right to the alternating series test. So here, I see I have that negative 1 to the n. I'm just asked if it converges, diverges. I'm not going to bother with the absolute convergence here. I'm going to jump right into the alternating series test. So we're going to look at the sequence n squared over n plus 4. Well, clearly that thing is always greater than 0, so the first point checks out. Second point, or probably even easier, the third point, I can show it break. So if I take the limit as n goes to infinity of n squared over n plus 4, well, that is going to infinity, and that is definitely not equal to 0. So the alternating series test fails here. Does not tell me that it diverges, but think about what the three tests are. Again, we're showing that they're positive, they are eventually non-increasing, and the limit is going to 0. Well, these bottom two, especially this last one, that looks a lot like the test for divergence, right? If this didn't go to 0, that series would diverge through the nth term test for divergence. So we're kind of dumb here. We started with the alternating series test, but a better test to start with is always the nth term for divergence. And we've never been able to just say if the limit of the sequence goes to 0, it converges. We've never been able to say that until now with these alternating series tests, just for the alternating series test. So what I should have probably started with, not the alternating series test, but the nth term test for divergence. If I take the limit as n goes to infinity, and I do have to take the full sequence here, that thing is going to plus or minus infinity. It is diverging because this thing is blowing up, right? Sure, the negative one is saying it's positive, negative. The fact is, though, it's going to the infinities. And so by the divergence test, or the nth term test for divergence, the series n equals 1 to infinity of negative 1 to the n times n squared over n plus 4 diverges. Easiest test there is. So don't forget about that divergence test. Just because you see an alternating series test doesn't mean we can't use the other test still. It's just the alternating series test gives us something really easy to do. Generally what we're going to see though is if the alternating series test doesn't play out, well then probably the divergence test would have played in to begin with. And so always a good idea, look at what the limit does to start with. If it goes to 0, we can't state using the divergence test that converges, but if we see that -1 to a power, we can use the alternating series test most likely to state that it does converge.